Hello everyone! Welcome to our deep dive into a chapter that might seem a little tricky at first, but I promise it's one of the most logical and rewarding topics in your Class 12 Maths syllabus. We are talking about inverse trigonometric functions. Now, you might be wondering why another chapter on trigonometry. You have already spent a lot of time learning about sine, cosine, tangent, and all their friends. Well, this chapter is like learning to read a familiar story backward. It's about finding the angle when you already know the trigonometric ratio. This skill is not just for scoring marks, it is a fundamental concept that will be your best friend in calculus, especially in integration and differentiation, which are huge parts of your board exams. Think of this chapter as a key that unlocks new doors in mathematics. Mastering inverse trigonometric functions will make many other complex topics feel much simpler and more intuitive. It's a relatively short chapter, but its importance is massive. The questions from this section are often straightforward and based on properties and principal values. If you understand the core concepts well, you can easily secure full marks on these questions, giving your overall score a significant boost. So let's start with the most basic question. What are these inverse trigonometric functions? Let's think about a simple trigonometric function like sine. When we write sin 30 degrees equals sine 1/2, what are we doing? We give the function an angle, 30 degrees, and it gives back a value, 1/2. It's like a machine. Input an angle, get a number. Now, what if we do the opposite? We know the value 1/2 and want the angle. That's where inverse trig functions come in. They find the angle when the ratio is known. So instead of sin theta equals sine value, we write sin 1 value equals sine theta. That little y1 is not an exponent or 1 sin. It simply means inverse sine. So sin 1/2 asks, which angle has sine 1/2? Answer, 30 degrees or P6. Similarly, inverse functions exist for cosine inverse tangent, inverse cosecant, inverse secant, inverse cotangent, inverse also called arcsine, arccosine, arctangent, and so on. They mean the same thing. Arcsine x equals sine sin 1x. It literally means the arc whose sine is x. Now, an important condition, to have an inverse, a function must be 1-to-1 and onto. 1-to-1 means different inputs, different outputs. But sine is not 1-to-1. Sin 30 degrees equals sine 1/2, sin 150 degrees equals sine 1/2, sin 390 degrees equals sine 1/2. Many angles give the same value, many to 1. That's a problem for an inverse. Sin 1/2, would have infinitely many answers. How to fix it? Mathematicians restrict the domain. Limit input angles so the function becomes 1-to-1 on that range. For sine, choose 90 degree to plus 90 degree. In that interval, every angle maps to a unique sign between 1 and 1. This restriction lets us define the inverse properly. That restricted range is the principal value branch, our next big idea. Now that we understand why we need to restrict the angles, let's talk about these special restricted ranges, which are officially called principal value branches. Every inverse trigonometric function has one. Think of it as an agreement among mathematicians worldwide. When we ask for sine inverse of 1/2, we could get 30 degrees, 150 degrees, and so on. To avoid confusion, we all agree to provide the answer that lies within a specific, predefined range. This unique answer is called the principal value. For sine inverse of x, the range is from minus pi by 2 to pi by 2, which is the same as minus 90 degrees to 90 degrees. So the principal value of sin circumflex 1/2, is pi by 6 or 30 degrees because it lies in the range. Each of the 6 inverse trig functions has its own principal value branch. It is extremely important to memorize these ranges. Let's list them out clearly. For e equals sine sin circumflex 1x minus pi by 2 to pi by 2, for y equals sine cos circumflex 1x 0 to pi, for y equals sine tan circumflex 1x, open interval minus pi by 2 to pi by 2, for y equals sine cosec circumflex 1x, minus pi by 2 to pi by 2 excluding 0. For y equals sine sec circumflex 1x, 0 to pi excluding pi by 2, for y equals sine cot circumflex 1x, 0 to pi. Once you have mastered the principal value branches, the next step is to learn the properties of inverse trigonometric functions. These properties are like superpowers that help simplify expressions fast. The first set of properties is quite intuitive. Sin arcsin x equals sine x, valid only if x, 1, arcsin sin theta equals sine theta, valid only if theta, P2, important condition. If theta is outside, use identities to find an equivalent inside the range. Next, negative inputs. These help find principal values. Arcs in x equals sign arcs in x, arctan x equals sign arctan x, arcsec x equals sign arcsec x. For those three, the negative just comes out. For the other three, arcos x equals sign pi, arcos x, arcsec x equals sign pi, arcsec x, arcot x equals sign pi, arcot x. Remember the two families, sin, tan, CSC, and cos, sec, cot. Another important group of properties is the reciprocal identities. Arcs in 1x equals sign RCC x, arcos 1x equals sign arcsec x, arctan 1x equals sign arcot x. They follow because the functions are reciprocals. Complementary angle properties, very elegant. Arcs in x plus arcos x equals sign P2, arctan x plus arcot x equals sign P2, arcsec x plus RCC sec x equals sign P2, valid across domains, useful to replace arcs in x plus arcos x with P2 in problems. Finally, sum and difference formulas, like tan a plus b, arctan x plus arctan y equals sign arctan x plus y, 1, xy. This holds if xy, 1, variations exist for xy, 1 or when subtracting terms. Now we get to the fun part, using everything we've learned to solve equations. Problems involving inverse trigonometric functions often look intimidating, but they usually boil down to applying the right property at the right time. The general strategy is to simplify the equation until you can isolate the variable. This often involves using one of the properties we just discussed to combine or change the inverse trig terms. For instance, if you have an equation with both tangent inverse terms, you'll likely need the tan circumflex 1, x plus tans 1, y formula to combine them into a single term. Let's try solving a simple equation. Suppose we have to solve tan circumflex 1, 2x plus tan circumflex 1, 3x equals pi over 4. This looks like a perfect candidate for the sum formula for tangent inverse. Applying the formula, tan circumflex 1, x plus tan circumflex 1, y equals sign tan circumflex 1, x plus y, 1, xy. Here our x is 2x and our y is 3x. So the left side becomes tan circumflex 1, 2x plus 3x, 1, 2x 3x. This simplifies to tan circumflex 1, 5x 1, 6x squared, equal sign pi 4. Now to get rid of the tan circumflex 1 on the left, take tangent of both sides. That gives 5x 1, 6x squared, equal sign tan, pi 4. We know tan, pi 4 equals sign 1, so 5x slash 1, 6x squared, equals sign 1. Cross multiply to get 5x equals sign 1, 6x squared. Rearranging gives 6x squared plus 5x, 1 equals sign 0. Solve the quadratic. Factorization works here. 6x 1, x plus 1, equals sign 0. That yields x equals 1 divided 6 and x equals sign minus 1. But we are not done. We must check validity. The sum formula assumes product 2x 3x equals sign 6x squared. 1. Check x equals 1 divided 6, 6 1 6, squared equals sign 1/6, which is less than 1, so x equals 1 divided 6 is valid. Check x equals sign minus 1, 6, 1, squared equals sign 6, which is greater than 1. Also tan circumflex 1 minus 2 and tan circumflex 1 minus 3 are negative angles. Their sum cannot be a positive angle like pi 4. Therefore x equals sign minus 1 is extraneous and must be discarded. The only solution is x equals 1 divided 6. You might be thinking, okay, I can solve these problems for my exam, but will I ever use this in real life? The answer is a resounding yes. Inverse trigonometric functions are not just abstract mathematical tools, they are essential in many fields of science, engineering, and even computer graphics. One of the biggest areas where you will use them immediately is in calculus. When you study integration, you will come across standard integrals whose results are inverse trigonometric functions. For example, the integral of 1 over the square root of 1 minus x squared is sine inverse of x, and the integral of 1 over 1 plus x squared is tangent inverse of x. Without knowing these, you would be stuck on many integration problems. In geometry and physics, these functions are used constantly to find angles. Imagine you are a video game developer designing a character that needs to aim at a target. The character is at a certain x, y coordinate, and the target is at another. You can calculate the horizontal distance, which is the adjacent side, and the vertical distance, which is the opposite side. To find the angle at which the character must aim its weapon, you would use the arctangent function. Angle equals tangent inverse of opposite over adjacent. This is used millions of times per second in video games, robotics, and navigation systems to determine orientation and direction. Think about architecture and engineering. When designing a bridge, a building, or even a simple ramp, engineers need to calculate angles very precisely to ensure structural integrity and safety. For instance, if you know the required height and length of a wheelchair ramp, you can use the inverse tangent function to calculate the necessary angle of inclination to meet accessibility standards. Similarly, in astronomy, scientists use inverse trigonometric functions to calculate the angular distance between stars, or the inclination of a planet's orbit based on observational data. It helps them map the vast universe from right here on Earth. Even in fields like electrical engineering, the concept of phase angles in alternating current circuits is analyzed using trigonometric and inverse trigonometric functions. The relationship between voltage, current, and impedance often involves finding an angle, and these functions are the perfect tool for the job. So as you can see, what you are learning today is a fundamental building block. As you prepare for your CBSE board exams, it's important to have a smart strategy for a chapter like this. My first and most important tip is to create a formula sheet. On a single page, write down principal value branches, write down the properties, write down the formulas we discussed. Keep this sheet handy whenever you practice. The more you look at it and use it, the faster you will memorize it. Don't just read the formulas, write them down yourself. The act of writing helps to solidify them in your memory. Second, always check the domain and range. This is the #1 source of silly mistakes in this chapter. When you solve an equation and get a value for x, check if it's valid for the original expression. When you find a principal value, double-check that your final angle is within the correct principal value branch. For example, sin inverse of sin of 2 pi